This mini lesson is going to go over how to solve systems of linear equations with substitution. Linear equations, we're dealing with straight lines, no curves at this particular point, and we're going to use substitution, which is something that you guys have been using to solve equations. I'm going to show you how to use substitution using something familiar, and then we're going to start to add in some more complicated types of problems. And throughout this, I'm going to connect graphs and tables with equations so you can see how they all connect. So let's imagine I have this system of equations. So I have two equations. Let's see, y equals 2x minus 2. And let's do y equals 4. So this is our system of equations, meaning there's two equations, and our goal is to figure out what the solution will be in order to make both of these equations true. Now this is actually something that you guys have been doing for a while. You're simply figuring out what is x going to be if y equals 4. But we do represent this with equations as well. So let's go ahead and graph it so you can make that connection, set up a table, and then I'll remind you what substitution means before we go into a little bit more difficult problem. So if we start with this here, y equals 2x minus 2, we know that this right here is our y-intercept, and this right here is our slope. So I'm actually going to extend my graph down a little bit so I get to that y-intercept, which would be at -2. Let's pull this down so we've got a little bit of room to work. And then my slope is 2, which remember we can also write 2 over 1 because we are looking at rise over run. So I'm going to start here. I'm going to rise by 2, run over 1. Rise by 2, run over 1. Rise by 2, over 1. Rise by 2, over 1. Rise by 2, over 1. Then I'm going to go ahead and draw a straight line. You can do it by freehand. I always like to try to find a straight edge and connect it as much as possible. It doesn't have to be perfect, but it's like to get it as close as possible. And then we've got y equals 4. Well, this is actually pretty straightforward. Y is always going to equal 4 no matter what x equals. So here's y equals 4 there, and it's actually going to make a horizontal line. All right, so we have this intercept here. This is actually our solution where these two lines intersect, and it's 3. X always comes first, and it's 4 here. So that would be our solution. That's using graphing. If I looked at my tables, I always like to have my x first, that's my independent, then my y. You can go ahead and choose just a few values for for x, and then we're going to, and this is where I said you guys have been doing this before, you're actually going to substitute that x into the rest of the equation. So we know y equals 2x minus 2. So literally all you're doing is substituting that number in for x. So 2 times 0 is 0, minus 2, y equals -2. Do the same thing here. You are substituting it in. All right. So when I use this word substitution or substituting, let me fix that, you know that what you are doing is you are replacing the variable with a particular number. But what we're going to find out in the next problem is it doesn't always have to be just a number. Let's go ahead and finish this. 2 times 1, that's 2, minus 2 is 0. 2 times 2 is 4, minus 2 is 2. 2 times 3 is 6, minus 2 is 4. 2 times 4 is 8, minus 2 is 6. And let's double check to make sure that we have all these points. So When x equals 0, y is negative 2. That matches that coordinate point. When x equals 1, y is going to be 0. That's the case at that point right there. When x is 2, y is going to be 2. And there it is right there. And so on. Go ahead and fill the rest of these out. So 3, 4, there's 3, 4, and 4, 6. All right. Now we do have another equation. We had y equals 4. What this means is it simply doesn't matter what x is going to equal. Y will always be 4. So our coordinate points are 0, 4, 1, 4, 2, 4, 3, 4, 4, 4. Now the whole point of finding a solution to a system of equations is figuring out where do those lines intersect. Because in this case, there's one place where they intersect, and that's going to be the one possible solution that will work for both of these at the same time. So we can see right here, we've got x equals 3, y equals 4. And right here, we've got x equals 3, y equals 4. So using tables, we can see that these are going to be the only times, this is going to be the only time where they both have a matching coordinate pair. Using a graph, we can see that. And then using substitution, and like I said, we've already practiced this. We know y equals 4. So I'm actually going to take this first equation, y equals 2x minus 2. I'm going to substitute 4 in, meaning I'm going to replace this y with 4, 2x minus 2, and then I'm going to go ahead and solve. So let me add 2 to both sides. 6 equals 2x. I want to isolate that x, so divide by 2, divide by 2. I've got x equals 3. So when y equals 4, x equals 3, giving us this coordinate pair as our solution. All right, let's get to one that's a little bit more complicated. This is a review of what you know, but connecting it to this concept. All right, so let's imagine I have the system of equations, and this time I'm going to say y equals negative 1/2 x plus 4, and y equals 3/2 x minus 4. We need to find where this would be true. I'm going to say what's more than likely going to be one place where it would be true. Say more than likely because we haven't necessarily graphed it out yet. We're looking for that one place where these two equations, if graphed, would intersect. So we could fill out a table, x and y equals negative 1/2 x plus 4, x and y equals 3/2 x minus 4. You could go ahead and substitute in values for x. That's our independent one. That's the one we get to choose. Negative 1, 0, 1. I could jump and go up to 4. Negative 1, 0, 1. Jump and go up to 4. Now, hopefully what you've realized is if I were going to try to figure out where they intersect using tables, going into this, theoretically, I have no idea what the possible answer is. So I'd have to choose a lot of different values before stumbling across the correct answer. That's a lot of work. It's almost like guessing and checking. So I'm going to say we're going to avoid doing that with tables, but this is how we would do it if we were to use a table. I personally like to use graphs as a way to check my work, but we don't always have access to something where we can graph it out accurately. So that's why we want to get used to substitution. But in this particular instance, we're just going to review that graph and make that connection. So our first equation here, I've got my y-intercept of 4. I've got my slope of -1/2, so that means down 1 over 2, down 1 over 2, down 1 over 2. Then my next one, I've got a y-intercept of -4 in this case. It'll actually be right down here. And it's got a positive slope, so it's 3 over 2, so it's up 1, 2, 3 over 2, up 1, 2, 3 over 2, up 1, 2, 1, 2, 3 over 2. And let's go ahead and actually connect those points. So this was my second line, right about here. And this was my first line, right about here. This point is where they intersect, so this point is the solution. X value would be 4, y value would be 2. That'd be the solution. Now again, we don't always get a chance to graph, and our solutions aren't always going to be super pretty, so you might not have a tool that gives you that really accurate point where they intersect if you have to graph by hand. This is why we want to get in that habit of substitution. Now this particular set or system of equations is actually really easy to set up using substitution, because here I am saying that y equals this equation and y also equals this equation. So if both of these equal y, if I could say if -1/2 x plus 4 equals y, which also equals 3/2 x minus 4, then I could just say these two are equal to each other. I'm going to go ahead and solve it down here. We should have plenty of room. So -1/2 x plus 4 equals, and I'm going to leave that y out this time, 3/2 x minus 4. And I'm just going to go ahead and I'm going to solve for x. So I want to isolate one x on its own on one of those sides and move everything else to the other side. It doesn't really matter if I move my 3/2 x off of this side or my -1/2 x off of this side. I like to get rid of negatives, so I'm going to go ahead and cancel this out by adding half of x, because -1/2 x plus 1/2 x will get us to 0. Whatever I do to one side, I do to the other. We like to keep everything nice and balanced. So I'm left with 4 on this side. 3/2 plus 1/2 is 4/2. X minus 4. I like to rewrite things to keep it nice and neat. I don't need to have that plus 0. I can simplify this 4 over half. So 4 equals 2x minus 4. Want to get rid of this addition of 4 on that side. Combine all my like terms. Get all my just plain numerical values over here. So I want to add 4. -4 and +4 make 0. Add 4 on this side. 4 and 4 make 8. Pull down that 2x. I don't want 2 x's, I want 1 x, so I'm going to divide both sides by 2. I'm left with x equals 4. Now that is not my whole solution, that's just the x value. I need the y value. So I'm going to take that x equals 4, and x equals 4, and I'm going to substitute it back into the equation. You can choose either of the equations because you're going to have one solution, one final answer, no matter which equation you choose. So you choose the one you are more comfortable working with. In this case, I'm just going to choose y equals -1/2 x plus 4. Y equals -1/2. I'm substituting that 4 in, as I said, x equals 4 plus 4. Y equals, well, half of 4 is 2, and negative times a positive, the signs are different, so the product is negative, so -2 plus 4, and then -2 plus 4 is the same as 4 minus 2, which is going to give me 2, so y equals 2. Hey, that matches what I have here. All right, let's go on to one more problem. And again, it's going to make it a little bit more complicated because instead of having it set up where y equals the rest of the equation, we're actually going to go ahead and practice it with some that are a little bit mixed up. Well, mixed up is maybe not the best way to call it. Let's see. So my system of equation is going to be x equals negative y. Actually, you know what, let's change that. I'm going to make it 4 minus 2x equals 2y minus 4. This is what I meant by mixed up. It's not in standard slope-intercept formula. And then my next one is going to be x equals 6 minus 3y. So we've already determined that by putting things in tables, we can figure out the answer, but it takes a lot of work. It's almost like a lot of guess and check. So we're not going to do that. We can see that we could graph these, but we would probably want to put both of them into slope-intercept formula. So y equals mx plus b, meaning I would have to rearrange these equations. I would have to rewrite them into equivalent equations using this formula. Maybe I don't want to do that. So I can use substitution instead. So sometimes your equations will be written even more complicated. You might have multiple x's, multiple y's. You have to combine like terms. So sometimes you will have to rearrange your equations. But the nice thing about this one is I've got one isolated variable. And as long as you have one isolated variable, you don't have to rearrange anything. You can use substitution because I know that x equals this. So wherever there's an x in this equation, I can simply write 6 minus 3y instead. So 4 minus 2, instead of x, I'm going to write 6 minus 3y. I'm going to keep it in these parentheses to start with, so I know that this is the x. I have replaced the x value. I have substituted it with 6 minus 3y. And I'm going to say equals 2y minus 4. And you might wonder, okay, why did we do that? Well, the idea is now I only have one variable in this equation. So I can actually solve for y now. So first thing I'm going to do is I'm going to simplify. So keep that 4 here. My next term is negative 2. I am subtracting 2, but remember I can talk about it as negative 2 when I'm discussing it. And if you remember, what we're going to do is we're going to distribute that to each of the things inside of these parentheses because I'm multiplying this negative 2, since it's outside these parentheses, by each of the terms inside of it. So negative 2 times 6 is negative 12. And negative 2 times negative 3y, negative times a negative is a positive, so positive 6y equals 2y minus 4. I'm going to combine my like terms. 4 minus 12 is negative 8. Leave my plus 6y equals 2y minus 4. I want to isolate my y, so I want all my y values, or my y's with their coefficients on one side, all my numerical values on the other side. So I'm going to subtract 2y from both sides. I could have subtracted 6y but from both sides, but I think that I like to deal with less negatives if possible. And if I did do minus 6, I'd have to deal with a negative. These cancel out, and here I'm left with 4y. Run out of room. It happens sometimes. Really should have had a nice blank clean piece of paper to write this all out. But I'm simply going to rewrite it over here. So I've got, pull down my 8, 6y minus 2y is 4y. Over here, 2y minus 2y cancel it out. So I'm left with that negative 4. Want to get this numerical value off this side, so I'm going to add 8, so they'll cancel out. Whatever I do to one side, I do the other. And remember that equal sign is where that wall is. Left with 4y here. 4y equals 4, right? Yep. Negative 4 and 8 is the same as 8 minus 4. Divide both of these by 4, and I'm left with y equals 1. Have I solved it yet? No, I just know what y equals. So y equals 1, I'm going to take it and I'm going to substitute it back into one of the original equations, whichever one that I think is easiest to find. I'm actually going to go with this second one because I want to figure out what x equals, and x is all on its own. So actually we're going to come down here, I'm going to rewrite that. This was my second equation. I am substituting that y equals 1 in, so I'm replacing this y here with 1. So x equals 6 minus 3. I like to keep things in parentheses when I substitute them. Reminds me I'm multiplying, so x equals 6 minus 3 times 1 is 3, so x equals 3. So my solution is x equals 3 and y equals 1, and that's my solution. And if I were to graph this, that is, in fact, my solution, which you could check using a graphing calculator, or you could put them both into slope-intercept form and check to see if where they intersect also gives you this solution.